So 152. Yeah. All right. So the next on the syllabus is number 158. So this is section 6.4. We're on Green's theorem. 158. So calculate the integral, line integral. And again, that circle there doesn't really mean anything in particular. It's just sometimes people use that for line integral. Calculate this p dx plus q dy along C, which is the triangle 0, 0, 0, 1, 1, 1. Did we do that one? Or was it the same as the last one? Yeah, it's the same as this one. So 2y, 2 times y plus x sine y. And then x squared cosine y minus 3y squared. So calculate the line integral over C. This is the vector line integral. So, in the book it's written like this, p dx plus q dy. So, I mentioned in the lecture, and we talked about last time, how that is just another notation for this. So that is not the scalar line integral. The scalar line integral is written like this. Okay, so it's just a function ds. There's no dx dy, it's just ds. There, this is p dx plus q dy. So that's a dot product. All right, it's the dot product of pq dx dt dy dt dt, like that. So that's the vector field, and that is r prime of t. Okay, so again, that's the vector line integral. Just a little notational discussion. Over C, where C is 0, 0, 1, 0, 1, 1. Oh, it's not quite the same one, isn't it? So 0, 0, 1, 0, 1, 1, and then here. In the counterclockwise direction, I expect. Yeah, oriented counterclockwise, using Green's theorem. Okay, so remember Green's theorem, that f dot dr, well, let me write it as p comma q dot dr over C, where C is a simple closed curve oriented counterclockwise, is equal to the double integral over R, which is the inside of C, qx minus p, qx minus py dA. Okay? So here, p of x, or p, is equal to 2y plus 2x sine y, and q is equal to x squared cosine y minus 3y squared. So py the derivative of this with respect to y is 2 plus, this 2x is a constant, so it's just 2x cosine y. And qx, derivative of q with respect to x, 2x cosine y. And then the derivative of that is 0 with respect to x. So by Green's theorem, right, and this is C right here. So this is equal to, by Green's theorem, the double integral over R, which is the interior of C, qx, 2x cosine y, minus py, 2 plus 2x cosine y dA. So it turns out to just be negative 2. Right? So this integral is what? Now, you don't actually have to set up the iterated integral type 1 or type 2, because since that's a constant, this double integral is equal to what? What's that double integral equal to? Well, conceptually, before you actually get the actual answer, what is it? Right, this is equal to minus 2 times the area of R. So it's minus 2 times a half, base times the height, which is 1 and 1. So the answer is minus 1. Okay. So it was 158. Next, 165. More of the same, probably. So probably we can do this on our own here. Use Green's theorem to evaluate this one, where C plus, they're using C plus suddenly, is the perimeter of the square 0, 1 cross 0, 1 oriented counterclockwise. So this one is, you know, you can do this one on your own. $165, $167. So use Green's theorem to, oh yeah, this is not a good problem, this one. This doesn't use Green's theorem. At least I don't. Use Green's theorem to find the area of one loop of the 4-leaf rows. I mean, this is just a polar integral calculation. It's not really, I'm not sure why they're getting into this problem here. So 167, we'll just omit that. It doesn't really use Green's theorem. 171. So evaluate why is this in the section on Green's theorem? Evaluate this where C is the boundary of the square from 0, 1 to 0, 1, traversed counterclockwise, but this is a scalar line integral. So why is this here? Why is this problem here? And well, they're saying that the answer is 3, but why are they presenting that with Green's theorem? Because that's a scalar. That is a scalar line integral. I'm not sure. So number 171, it doesn't use Green's theorem. Because it is a scalar line integral. So we'll just leave that one out. 173, 184. So evaluate, so this is P dx plus Q dy, just written in a strange way. So let's take a look at that. So evaluate, so x dx plus y dy over x squared plus y squared over C, where C is any closed curve traversed counterclockwise. So it must be that it's 0. Piecewise smooth simple closed curve enclosing the origin and traversed counterclockwise. Well, I see. You can't actually use Green's theorem here because with Green's theorem, you do actually need to have that contains the origin. Right, so with Green's theorem, you do actually have to have that things are continuous inside the simple closed curve. So here's the formal statement of Green's theorem. Given a two-dimensional vector field F and a simple closed curve C oriented, well, I didn't write that, and it has to be continuous here, but I believe it does. Where's the formal statement of Green's theorem? Continuous, right? Continuous partial partial derivatives on D. So because the origin, so this does contain the origin or doesn't contain the origin? I mean, they don't give you what the curve is. They don't give you what the curve is. Enclosing the origin and traversed counterclockwise. Any piecewise smooth, simple closed curve enclosing the origin. So, I mean, you can't use Green's theorem, so which piecewise closed curve are they talking about? Right, because, so this looks like this. This is the line integral over C, so it's x over x squared plus y squared, comma, y over x squared plus y squared, like that. Right, because this distributes, this denominator distributes over the addition. Or over the numerator, the addition in the numerator. C is any simple closed curve. So if they mean that, they must mean, let's take C to be, the circle of radius 1. Right, and we can't apply Green's theorem here. Because P and Q are not continuous at the origin. Right, because we have this division by 0 at the origin. It's continuous everywhere else, but not at the origin, so we can't apply the Green's theorem here. So we'll take C to be the circle of radius 1, so r of t is equal to cosine t, comma, sine t, 0 less than or equal to t, less than or equal to 2 pi. So r prime of t is minus sine of t, comma, cosine of t. So the line integral here, so the integral over c of x over x squared plus y squared, comma, y over x squared plus y squared dot dr is equal to the integral from a to b f of r of t dot r prime of t dt. Okay, so we'll calculate this. So this is 0 to 2 pi. So f of r of t, this is, so x is cosine. And then x squared plus y squared is just 1. Y is sine. And x squared plus y squared again is just 1. Dot r prime of t minus sine of t cosine of t dt. So this is equal to the integral from 0 to 2 pi minus cosine t sine t plus cosine t sine t dt, which is 0. And if we were to apply Green's theorem, so it's q py minus qx. Suppose we were to have tried to apply Green's theorem. It shouldn't work, but it is working for some reason. To calculate the double integral over r of qx minus py dA. What do we get? Well, p was equal to x over x squared plus y squared, and q was equal to y over x squared plus y squared. So py is equal to, so it's minus x over x squared plus y squared times 2y. So that's equal to minus 2xy over x squared plus y squared squared. And qx, I imagine, is going to be the same thing. Well, therefore, the double integral over r of qx minus py dA is the double integral of 0, which is 0, of course. So for some reason, the two things are still the same, even though you can't apply Green's theorem. So what the point of the exercise is, I'm not sure. Two pi. Did we calculate something wrong here? Minus sine t cosine t plus sine t cosine t. What happened here? So this is cosine over cosine squared plus sine squared. Sine over cosine squared plus sine squared. Do I have this backwards? X dx, y dy. And then r prime is minus sine t cosine t. So this is f of r of t. And that's r prime of t. So the dot product is minus sine times cosine plus sine times cosine, which is 0. So how are they getting 2 pi? How are they getting 2 pi? Cosine t, sine t. So that's x dx plus y dy over x squared plus y squared, traversed counterclockwise. F of r of t dot r prime of t. So this is cosine over cosine squared plus sine squared. So that's just cosine. And then sine over cosine squared plus sine squared. So it's 1 again. And r prime is derivative cosine is minus sine, derivative sine is cosine. Dot product is minus sine times cosine. I'm unsure what there. Traverse counterclockwise. It's not 2 pi, it's 0. Do they mean to switch these? If it was y dx plus x dy, then if there was a y here and an x there, well, negative y here and x there, then you would get not a 0 here, but sine squared plus cosine squared, you'd get 1, in which case the integral would be 2 pi. Yeah, so the so they have a typo in the problem, right? If they had this, if they had minus y comma x, then the answer would be 2 pi. As would the answer here. They would be the same, which they still are, but you can't apply Green's theorem here. So somehow this is just a coincidence that they came out to be the same, but I'm not sure what the point of the exercise is otherwise. All right. So 184, next problem. Use Green's theorem to evaluate the line integral x squared y dx minus xy squared dy, where C is the circle of radius 2 oriented counterclockwise. So the point of like 184 is that when you apply Green's theorem, you will have to probably transform to polar coordinates. Or maybe not, we'll see. So calculate x squared y minus xy squared dot dr over c. So p is equal to x squared y, q is minus xy squared. So py is x squared, and qx is minus y squared. So, via Green's theorem, this becomes the double integral over r, which is the interior of the curve, qx minus py dA. So this is equal to negative the double integral over r, x squared plus y squared dA. So now that we've got the double integral from the application of Green's theorem, now the question is, like, how do you want to calculate it? Okay, so now let's transform xy to r theta, polar coordinates. So we're transforming the rectangular coordinates to polar coordinates, and this, of course, is just the polar rectangle, r going from 0 to 2 and theta going from 0 to 2 pi. So this is negative double integral, or the iterated integral, from 0 to 2, 0 to 2 pi. X squared plus y squared is r squared. And then the dA becomes r dr d theta. So negative integral from 0 to 2 pi, integral from 0 to r to the third dr d theta. So minus 1/4 r to the fourth, 0 to 2 d theta. So this is equal to 16 over 4, so minus 4 d theta. That's a constant, minus 4, so it's minus 4 times 2 pi, which is minus 8 pi. Okay, so the point of that exercise is, first we applied Green's theorem. So we're asked about this vector field line integral over C, where C is this simple closed curve. Okay, and these functions, p and q, they're polynomials, so they're continuous everywhere in the xy plane. So we apply Green's theorem. So this is equal to partial derivative qx minus partial derivative py, which turns out to be minus y squared minus x squared dA, over the region R, which is the interior of the circle. So now, how do we want to calculate that? Probably the best way to calculate something over a disk is to use polar coordinates. So we transform to polar coordinates and calculate as usual. (184) 201 and 204. Now, 201 and 204 are about this other type of line integral, which we're not going to do. So 201 and 204, we'll omit these. So there's another type of vector line integral, that's the vector flux line integral, but we're not going to cover that. when we get to surface integrals, we're going to cover vector flux over surfaces, but we're not going to do it with curves. All right, so section 2.5 or 6.5, just a quick overview of that. So it's just a section introducing curl and divergence. Okay, so number 214 is the first problem, and it asks, for the following exercises, just find the curl. So we have F. So the curl of a vector field is just for three-dimensional vector fields. So in this case, we've got 3xyz squared. So calculate curl of F, where F is equal to 3xyz squared, comma, y squared sine z, comma, x e to the z, or e to the 2z. Right, so the curl of F is equal to the 3 by 3 determinant. So, well, it's a cross product, of course, right? It's the cross product of this vector with F. This vector is the vector of partial differential operators in 3 dimensions. Partial with respect to x, partial with respect to y, partial with respect to z. 3xyz squared, 3xyz squared, y squared sine z, and x e to the 2z. So this vector del cross F. So this is equal to, so in the x-coordinate, it's the partial of y with respect to, the partial derivative with respect to y of this function, which is 0, minus the partial derivative with respect to z of this function. So we have 0 minus y squared cosine z. And in the j-coordinate, it's negative partial with respect to x of this function, which is just x e to the 2z, minus partial with respect to z of this function, 6xyz. And of course, we're going to negate that difference. And in the k-coordinate, you've got this 2 by 2 determinant. The partial derivative of this with respect to x is 0, and the partial derivative of this with respect to y, which is 3xz squared. So we get minus y squared cosine z, 6xyz minus x e to the 2z, comma, minus 3xz squared. So that's the curl. They go to some lengths to, try to explain what the curl is. To try to explain what the curl is, like in terms of, cyclic actions of vector fields. It never really quite makes sense, because that's not really what it is. What it really is it's part of Stokes' theorem. So when we get to Stokes' theorem, so Stokes' theorem is often called the curl theorem. Stokes' theorem gives what the meaning of the curl is, why it's there. So hopefully we get the Stokes' theorem on Monday next week. Well, next time, if not, yeah, next time. All right, so that was 214. 217. Calculate the curl of this one. Where f is equal to x minus y minus z minus x. So it is I, j, k, x minus y minus z, partial with respect to x, partial with respect to y, partial with respect to z, x minus y minus z minus x. So partial of this with respect to y is 0, minus partial of that with respect to z, which is negative 1. So since we're subtracting, it's 1. Here, partial of this with respect to x is negative 1, minus partial of that, which is partial of that with respect to z, which is 0. So it's negative 1 minus 0 is negative 1, but then again, we got to negate it. So it's positive 1. And then k, partial of this with respect to x, minus partial of that with respect to y, which again is 1. $226, anything interesting there? Just find the divergence of this same vector field. So it was the same one, wasn't it? X minus y minus z minus x. So the divergence of f, where f is equal to x minus y minus z minus x. And just to remind you, the divergence of f is this gradient vector del dot product with f, right? Where del is the vector of partial differential operators with 3 variable functions. So here the divergence of f is equal to, well, partial derivative of this with respect to x, which is 1, plus the partial derivative of this with respect to y, which is 1, plus the partial derivative of this with respect to z, which is 1. So it's just 3. Notice the divergence is a scalar function, right? Curl of a vector field is another vector field. The divergence of a vector field is a scalar function. In this case, it's just, a constant, 3. Another example of divergence. 227, 232. So x over square root x squared plus y squared, and y over square root x squared plus y squared. So that is a 2-dimensional vector field, but it can always be placed in 3 dimensions by just sticking on another coordinate here, which is 0. Okay, so in 227, all right, F is a 2D vector field, but it can always be placed in 3D by making the third coordinate 0. Right, so in this case, f of x, y, z is x over square root x squared plus y squared, y over square root x squared plus y squared, 0. So in this case, the divergence of f, well, it's the partial derivative with respect to x of this, plus the partial derivative with respect to y of this, plus the partial derivative with respect to z of 0, which of course is 0. Right, so this is equal to, so this is, I guess we might as well use the quotient rule here. So it's the derivative of the top times the bottom minus the derivative of the bottom times the top. So the derivative of the bottom is x over x squared plus y squared. So derivative with respect to x of like 1 plus x squared, that's x over square root 1 plus x squared. So just quick shortcut there. So square root 1 plus x squared, the derivative with respect to x of that is x over square root 1 plus x squared. So this is just like that, except, you know, instead of a 1, we've got the y squared, but it's still just a constant. So the derivative of the top times the bottom minus the derivative of the bottom times the top, so that becomes a squared, all over the bottom squared. Here, similar sort of thing. Plus 0. So this must simplify, so it becomes x squared plus y squared minus x squared over square root there. So what do we have here? So this is equal to y squared over x squared plus y squared to the 3/2 minus x squared over, so y squared minus x squared over x squared plus y squared to the 3/2. Oh, this is a plus, and how did that become a minus? So it's just 1 over square root x squared plus y squared. So y squared plus x squared. Oh, I added these. I forgot to add that. Yeah, this step wasn't right here. So this is 2. No, wait a minute. No, I did that right, didn't I? Right, when I add these together, it becomes x squared plus y squared over square root x squared plus y squared minus x squared. No, this is correct. So it's just 1 over x squared plus y squared. Square root x squared plus y squared. The only other sort of special thing to remember about curl and divergence is that a vector field is conservative when a three-dimensional vector field is conservative when the curl is, if and only if the curl is 0, as long as you've got continuous first partial derivatives in the vector field. So are there any exercises that deal with that? That was number 227, 232, 242. 232, we don't need to do that. Find the curl of f. You don't need to do that. We've already done stuff like that. 246, 252. Find the divergence at the given point. No point in doing that. Find curl at a given point. No. So the rest of the problems in this section, so numbers 227, 232, 242, 246, 252, and 254, we can omit those. Okay, so all that we really need to know about curl and divergence are just what they are, so that when it comes time to apply them, which is in section 6.7 and 6.8 for Stokes' theorem and the divergence theorem, that we know what they are. Curl is also useful for telling when a three-dimensional vector field is conservative, but I'm not gonna test you on that. Okay, so next section is the section on surface integrals. So let's take 5 minutes, 7:30. So let's come back at 7:35. So we'll come back at 7:35 and we'll get into section 6.6. Okay, we're back. So moving on to section 6.6 on the two types of surface integrals. There is the scalar surface integral and the vector surface integral. Just like how there is with line integrals, there's the scalar type and then there's the vector field type. But one topic that is missing, which we covered in the lecture, okay, is parameterizing a surface. So writing a surface parametrically. So that's what the first few exercises in this section. Okay, so first one is number 274. So find parametric descriptions for the surfaces. So here we've got the paraboloid z equals x squared plus y squared for z from 0 to 9. So section 6.6. So 274. So parameterize the paraboloid z equal to x squared plus y squared for 0 less than or equal to z less than or equal to 9. So that's that standard paraboloid there. Right, like that. And going all the way up to z equal to 9. All right, so the shadow of this parabola down in the xy plane, if you shine the light straight down, is the intersection of the plane z equals 9 with the surface and then everything that's inside of it. So that, of course, is where x squared plus y squared equals 9, which is the circle of radius 3. So here are two different parameterizations. So so the easiest one to work with usually is the standard parameterization. The standard parameterization, which is r of x, y, where x is x, y is y, and z is f of x, y. Because the surface is, of the form z equal to fxy, z equal to fxy, you've always got this standard parameterization. X is x, y is y, and z is fxy. For x and y, in the circle of radius 3. More right here, I guess. All right, so for all x, y in the circle of radius 3. So if you take the surface and you shine a light straight down along the z-axis, the shadow it makes, this paraboloid in the xy plane, is the shadow of this circle up here, which is the circle x squared plus y squared equal to 9. Right, and everything inside of it. So that's the circle of radius 3. So standard parameterization, always a good choice if you can use it. And then there's also for this one, the parameterization that goes along with revolving a curve around the z-axis. So if you look at this curve here, so here's a t-axis, and here is the curve square root of t. So now if I revolve that around the t-axis, to get paraboloid. Right, it's actually not t squared, it's square root of t. So in that case, the parameterization is, so I'm going to make the t-axis the z-axis, right? We're going to do this rotation So revolve around the t-axis to get the paraboloid, and then identify t with z. So the t goes in the z coordinate because we're going to change the t-axis to the z-axis to get that surface of revolution there along the z-axis. So the z gets identified with t, and then the x and y are f of t cosine theta, f of t sine theta. Just really messy here. F of t cosine theta, f of t sine theta, and then that was t. And then this is supposed to go up to where? Up to t equal to 9. Well, up to z equal to 9, so 0 less than or equal to t, less than or equal to 9, because t gets identified with z. And then since we're going to do the full rotation around the axis, 0 is less than or equal to theta is less than or equal to 2 pi. All right, so that's the second parameterization that you could use. So two different parameterizations. Sometimes one parameterization, the calculation might work out a little more easily. So it's 274. Next problem, 276. So for the following exercise, you have to find a parametric description of the surface. The frustum of the cone z squared equals x squared plus y squared for z between 2 and 8. So z equals square root x squared plus y squared, 2 less than or equal to z less than or equal to 8. So this is that standard cone whose sides have angle 45 degrees, but we're only doing, from 2 to 8 in the z coordinate. So that's starting like here, and we're going up to here. So just part of that cone. Okay, and leaving out this bottom bit. Okay, so again, two parameterizations. So one, standard parameterization, Rx, Y, because it's Z equal to Fxy, X is X, Y is Y, and Z is Fxy. And what is the domain for X and Y in this case? Well, the domain for X and Y is the shadow this surface makes when you shine the light straight down. The shadow it makes in the xy plane. Well, that's the circle of 2, radius 2. That's the circle of radius 8. So the domain for x and y is all the points that are inside this this ring. Annulus would be the technical term for the thing. All right, because you're going to be missing out this donut hole there, right? This is where z is equal to 8 up here. And this is where z is equal to 2 down in here. So 2 to 8. Right, this is where 8 is equal to the square root of x squared plus y squared. In other words, the circle of radius 8. Here, 2 is equal to the square root of x squared plus y squared. In other words, the circle of radius 2. All right, and then this rotational thing. So again, this cone is the slope of the sides is 45 degrees. Right? If you let x equal 0, you get z is equal to plus or minus x. So z is equal to plus or minus x. That's the line of slope 1 in the y, or plus or minus y. So that's the line of slope 1 and slope negative 1 in the yz plane. So that's, you know, just the standard function like that. So this is the t-axis, and this is the whatever axis here. So t is equal to f of t. So this rotational scheme is f of t cosine theta. So it's t cosine theta, t sine of theta. And then, again, we're rotating around the t-axis, or the z-axis, so t gets identified to z. 2 less than or equal to t less than or equal to 8. And, of course, we're going all the way around, so theta goes from 0 to 2 pi. So that is your second parameterization. You'll notice that in the second parameterization, the region over which we are doing which is the domain for the parameterization, is just a rectangle, right? T goes from 2 to 8, and theta goes from 0 to 2 pi, right? It's not this. You know, this region is probably going to have to be switched into polar coordinates at some point. Okay, this region is probably not going to need such a conversion. Anyway, it doesn't matter really. I mean, whichever one works better for you, that's the one you use. 278. A cone with base radius r, height h, where r and h are positive constants. So we want to parameterize a cone. Find a parametric description of such a surface. So a cone with base radius r, height h, and of course r and h are positive. So parameterize the cone obtained, well, this cone. So the base radius here is r, and the height here is h. Well, of course, this can be done. I mean, you can do it similar, like to what we did in the last problem, but here I think the rotational scheme is definitely a little easier. So let this be r on the vertical axis, and let this be h on the t-axis. So this is the line whose slope here, so the slope is rise over run, so minus r over h, right? So the linear function here is f of t is equal to minus r over h t plus the y-intercept, which is r. Well, the vertical intercept is r. Right, so rotate this around the t-axis. To get the cone. And you can, you can identify that axis with either X, Y, or Z. So this is going, I guess we'll just do Z, right? So we'll make this the Z axis. So make H the Z axis. So we'll get minus R over HT plus R. I guess we'll write it like this. R minus R over HT cosine theta, comma, R minus R over H T, T sine theta, and then T. 0 less than or equal to T less than or equal to H, 0 less than or equal to theta less than or equal to 2 pi. You can also set up some kind of cone. Z is equal to, some constant with the x squared plus y squared going on there, but I think it's clearer this way. Okay, getting the slope of the side correct. It's easier with this rotational type setup. Yeah. So that was 278, 281. So for the following exercises, let S be the hemisphere. So the upper hemisphere of the sphere of radius 2, and evaluate each surface integral. So for 281, so calculate the scalar surface integral over S, Z ds, right? Where S is equal to the upper hemisphere of the sphere of radius 2. Okay, so the first thing you need to do is to get a parameterization for that upper hemisphere. Different ways to do it. There are different ways to do it. What do you guys think? There's one choice that's kind of natural, although I believe the calculation is going to be real nasty. Well, the calculation's nasty this way too. Gosh, is there an easier way to do this? I think maybe we'll just try the standard parameterization, because these other parameterizations just look really bad. The way I did them before. Alright, so first we parameterize, and because it's just the upper hemisphere, right, this is z equal to 4 minus x squared minus y squared. Right, so Rx y is equal to, well, x is x, y is y, and z is square root 4 minus x squared minus y squared. Okay, and the domain for x and y is, the shadow this casts in the xy plane, which is the disk of radius 2. For xy and the disk of radius 2. Right, okay, so remember the form for the surface integral. Okay, so the surface integral f x y z ds is equal to, well, it's the double integral of f of r of x, well, u and v, partial derivative ru cross partial derivative rv, the length dA. Right, so u and v are the variables you're using for your parameterization. Right, so it's the function f, along the surface, r given by ruv. So here we have rxy, so u and v are x and y. And then you take the partial derivatives, r with respect to x, r with respect to y. You take the cross product and calculate the length. And it's the double integral of this scalar function, dA over r. Okay, so a lot of calculations that are happening inside there, but let's go through. Okay, so partial derivative of r with respect to x, well, that's 1. This is 0. And this one is, well, without going through a lot of time here, it's just this. That's Rx. Ry is equal to 0, 1 minus y over 4 minus x squared minus y squared. All right, partial derivative with respect to y here is 0. Partial derivative with respect to y here is 1. Partial derivative of this thing with respect to y is that. So now we calculate the cross product, and you can do the cross product either Rx cross Ry or Ry cross Rx. Doesn't matter in this context because we're just going to take the length of that, and the length stays the same no matter which cross product you choose. So Rx cross Ry, so that's 1, 0 minus x over, this is 0, 1 minus y over square root so this cross product is in the x coordinate. You've got this 0 minus that. So x over square root 1 minus x squared minus y squared. In the y coordinate, you have this minus 0. So this minus 0 negated is that. And then in the k coordinate, you just get 1. So that is Rx cross Ry. So the length of Rx cross Ry is equal to square root of this squared plus this squared plus that 1 squared. This is probably going to simplify, so we've got x squared plus y squared plus 1 minus x squared minus y squared over that. So these cancel, so we get 1 over square root 1 minus x squared minus y squared. So that's Rx cross Ry. So the surface integral, oh, and where's f? Fx, y, z. Fx, y, z is just z. So f of r of x, y. So x is x is x, y is y, and z is this. Oh, did I change my 4 into a 1 during this calculation? I did. Those are 4s. 4, 4, 4, 4, 4, 4, 2. Okay. So we've got everything we need now, right? So the scalar surface integral z ds is the integral, double integral. So surface integral we write with, as a double, using the double integration symbol because, a surface is a two-dimensional domain. But, again, this is the notation for a scalar surface integral. It turns out to be, right, and that's why we have the ds there. It turns out to be the double integral over r of f of r of uv, ru times ru cross rv dA. So in this case, it's the double integral over r of, so this is a 4 minus x squared minus y squared, square root. This is the rx cross ry, so 2 over, oh, we didn't even, crazy. So it's just the double integral over r of 2 dA, which is 2 times the area of r. And what was r? Oops, go away. What was r? R is the circle of radius 2, right here. So pi times r squared, so that's 2 squared is 4, so it's 8 pi. So I did this last time with 2 different parameterizations. I used like the rotational scheme to parameterize, and I also used like the spherical coordinates scheme to parameterize, and both of those calculations were nasty. In particular, that cross product was nasty, but this one was much easier. So there was 3 different ways to parameterize that, and I picked the 2 harder ones. All right. Now, it doesn't matter which way you do choose, however, because the answer you get will always be the same, no matter which parameterization you pick. Not that the calculation will be the same difficulty. It could be a lot harder in one or the other. Okay, 283 is the next one. So, is that z supposed to be there? Yeah. All right. So in 283, same surface, but now we've got the double integral over s of x squared plus y squared. So 283, so same surface as 281. Calculate double integral or surface integral z x squared plus y squared ds. So using the same rxy, as in 281, okay, rx cross ry, partial derivatives, was 2 over square root 4 minus x squared minus y squared. Okay, and now f of x, y, z is z times x squared plus y squared. So f of r of x, y is equal to z. So using the same so that was x is x, y is y, and z is that, as in 281. So z is this square root, and x squared plus y squared is just x squared plus y squared. So now the scalar surface integral z x squared plus y squared ds is the double integral over r of f of r of x, y times rx cross ry length dA. So double integral over r. This is x squared plus y squared square root 4 minus x squared minus y squared times this cross product length dA. So those cancel. So we get 2 times the double integral over r x squared plus y squared dA, where r is, again, the circle of radius 2. All right, so r is equal to the circle of radius 2. So now you do actually have to convert. So this is a double integral. So now we'll convert to polar. Right, because we do actually have to do, because that's not just a constant this time around. We actually have to do some work here. So r goes from 0 to 2, and theta goes from 0 to 2 pi. So this is 2 times the integral from 0 to 2 for r. Let me go down the page. So 2 times the integral from 0 to 2, and 0 to 2 pi, x squared plus y squared is r squared, r dr d theta. So 2 times integral from 0 to 2 pi, integral from 0 to 2, r to the third, dr d theta. So 1/4 times 2 is 1/2. R to the fourth from 0 to 2. So 16 over 2. So this is 8. Integral from 0 to 2 pi of, 1 d theta. So that's just 2 pi. So in the end, we get 16 pi. Okay, so 281 and 283, we use the same surface, but, two different functions. Okay? So this is a couple nice problems. So, what can you expect on the exam for Chapter 4? For sure, one problem is going to be calculating one of these surface integrals, scalar surface integrals, right? We had scalar line integrals, and we had scalar surface integrals. Okay, so, and the only way to calculate them is straight from the definition, the way we've been doing it. Okay, so, so you're going to have one problem where you're going to calculate a scalar line integral, and one problem where you're going to calculate a scalar surface integral. And there's no theorems to help about that. There's just calculating it straight from the definition, and that's it. With the vector line integrals and the vector flux surface integrals, there are theorems that can help out in different situations. There's Green's theorem for line integrals. There's Stokes' theorem, divergence theorem for surface integrals, vector flux surface integrals. But you can't always apply them, nor can you always apply Green's theorem because you need a simple closed curve for Green's theorem. So with this, we'll talk more about exactly which problems, to expect with the vector line integral and the vector surface integrals. But with the scalar, the only question to expect is, well, here's a surface integral calculated. Here's a line integral calculated. All right, so it was 283. Next is 286. All right, so for the following exercises, okay, evaluate f dot n. So there's two, there's several ways that the vector flux surface integral is denoted. There's this f dot n ds for vector field f, and n being the unit normal vector. So that's one notation. That's what they're using here, and they should get rid of all the space here. So for 286, we're calculating the vector flux surface integral, where n is pointing upward. Right. So you've got an oriented surface when you're calculating vector flux. You have side 1 to side 2. So this time n is pointing upwards. So you're flowing from the bottom side of the surface. So this is the surface in this picture here. The bottom side of the surface to the top side of the surface. You're measuring the flow in that direction, in the upward direction across the surface, rather than the downward direction. Okay. So as long as the surface isn't completely vertical, then that makes sense, going from bottom to top. So x squared, y squared, z squared. So f is x squared, y squared, z squared. Calculate. So they're using the surface integral of the scalar function f dot n ds, where n is that unit normal thing, unit normal vector function, i.e. just f dot ds, where s is the oriented surface. I like this notation better. Anyway, doesn't matter so much. Where S is the upwardly oriented surface, plane, right, z equals y plus 1 that's inside the cylinder. So you've got that cylinder. That's not the surface, though. The surface is the plane. The plane that's inside the cylinder. So this is S oriented upward. What is the point of the cylinder? What does it do for you? What does the cylinder do for you? Right? Well, the plane is z equals y plus 1, so standard parameterization. R, X, Y, X is X, Y is Y, and Z is Fxy, so Y plus 1. What does the cylinder do for you in this case? Right? The domain for the parametric function, for the vector function that defines that surface, is the shadow that the surface casts when you shine the light straight down the z-axis. So what's the shadow in the xy plane? Well, if you take the whole plane, z equals y plus 1, and you shine the light down, it covers the entire xy plane. So obviously that's not it. Which part of the surface are we looking at? Just the part of the surface in the cylinder. Just this blackened part. So the shadow in the xy plane is that. Right? So for xy in the circle of radius 1. So that's R right there. So when you say the part of the plane that lies inside the cylinder, so we're measuring the flux across the cylinder. That's a beautiful picture they have in the book here. We're measuring the flux, not across the cylinder, across the plane, not across the cylinder, across the plane. But what part of the plane? You can't measure it across the entire plane, right? Because, I mean, you can, that would be an improper integral, right? You need to have some sort of finite measure domain. So we're just talking about the oval-shaped part of the plane that lies inside that cylinder. So we're not doing the flux across the cylinder, it's flux across the plane, but just the part of the plane that's inside that. All right, so now we need those partial derivatives. Rx, partial derivative r with respect to x, 1, 0, 0. Ry, 0, 1, 1, like that. And now we're talking about the upward orientation of the surface. Right, so our surface is, again, this oval shape here. And it's oriented up. Now, the partial derivative of r with respect to x is in that direction. The partial derivative of r with respect to y is in this direction. So which cross product do we want to point the surface up? Rx cross Ry or Ry cross Rx? Well, to point the unit normal vector up. Rx cross Ry or Ry cross Rx? Well, you take your right hand and you curl your fingers in the direction from X to Y, and your thumb needs to be pointing up. Right? So, if you take the fingers of your right hand, and if you curl them in the direction from X to Y, then your thumb points up. Right? So if your fingers are pointing this way, then your thumb is pointing up, of your right hand, right? So it's Rx cross Ry. If your fingers are pointing this way and you're using your right hand, you're curling your fingers in the direction from Y to X, and your thumb is pointing down. So that's the wrong cross product. So here we're looking at the cross product, Rx cross Ry, to get the upward direction for the unit normal vector. So that's I, J, K, and nicely enough, these are constants. So this is 0, -1, 1. Right, so now the vector flux surface integral x squared y squared z squared dot ds is the double integral over r of f of r of u v dot ru cross rv dA. So you take the cross product and you take the dot product with f of r of u v. So, well, what was f? Sorry. So now f was x squared, y squared, z squared. So f of r of x, y, well, x is x, so x squared is x squared, y is y, so y squared is y squared, and z is y plus 1. So z squared is y plus 1 squared. So here, this is equal to double integral over r, x squared, y plus 1 squared, dot 0, -1, 1 dA. Evaluating that dot product, so this is minus y squared plus y plus 1 squared dA. So that's double integral over r. So this is y squared plus 2y plus 1 minus y squared. So that's 2y plus 1 dA, where r is the circle of radius 1. So that's 0 less than or equal to r less than or equal to 1, 0 less than or equal to theta less than or equal to 2 pi, right? You're going to have to convert to polar coordinates here. Can't really see any other way to do it. So this is equal to the integral from 0 to 1 for r, 0 to 2 pi. 2y is 2r sine theta plus 1 r dr d theta. So this becomes integral from 0 to 2 pi 2 r squared sine of theta plus r dr d theta. Oops, 0 to 1. Antiderivative for r, so that is 2/3 r to the third times sine theta plus 1/2 r squared. R equals 0 to r equals 1 d theta. So that just becomes integral from 0 to 2 pi, 2/3 sine of theta plus a half d theta. Well, this integral is 0. Integral from 0 to 2 pi of sine theta is 0. Right, because this area and this area cancel each other out. So it's just 1/2 times 2 pi. So you get pi. Okay, so that's the flux of that vector field across that oval-shaped surface. All right. Next problem on the list. So that was number 286. So next, 292. So evaluate so we went from vector back to scalar, but here it's just doing the calculation quickly for a surface that you're given. So evaluate the scalar surface integral x plus y plus z ds over s, where s is it's this parametric thing, but because these are linear functions with u and v, it's just a plane, and they're giving you a picture of it right there. For u from 0 to 1 and v from 0 to 2. So just a quick calculation. So you got r of uv is 2u plus v, u minus 2v, u plus 3v, 0 less than or equal to u less than or equal to 1, 0 less than or equal to v less than or equal to 2. Right, so calculate over s. Okay, so again, we need to know those partial derivatives. Partial derivative of r with respect to u is 2, 1, 1. Partial derivative of r with respect to v is going to be 1 minus 2, 3. So ru cross rv is going to be equal to I, j, k, 2, 1, 1, 1 minus 2, 3. So this is 3 plus 2 is 5. And then this is 6 minus 1 is 5, and you're going to negate it. And then in the k, you've got minus 4 minus 1 is minus 5. So the length ru cross rv is 5 square root of 3. Okay. So now the surface integral, scalar surface integral, x plus y plus z ds is equal to the double integral over r f of r of uv times ru cross rv length dA. So this is the double integral over r. So x plus y plus z. I guess we didn't calculate that one yet. Let's do that. So f x, y, z is equal to x plus y plus z. So f of r, u, v, I guess we need some more space for this. Is equal to, so x is 2u plus v, y is u minus 2v plus z is u plus 3v. So this is equal to 2u plus u plus u, so that's 4u plus v plus 3v minus 2v, so 4u plus 2v. So this is 4u plus 2v times this one was the square root of 3 dA. And what was r? It's the integral, r was the rectangle, u goes from 0 to 1, v goes from 0 to 2, right here. So this is the iterated integral, u going from 0 to 1, v going from 0 to 2. I'll bring that square root of 3 out front. 4u plus 2v du dv. U is from 0 to 1, v is from 0 to 2. So antiderivative with regard to u, so that's 2u squared plus 2uv, u equals 0 to u equals 1 dv. So that's the square root of 3 times integral from 0 to 2. 2 plus 2v dv. So that's square root 3 times 2v plus v squared. V equals 0 to v equals 2. So at 0 you get 0, and then at v equals 2 you get 4 plus 4. So it's, in the end, 8 square root 3. Oh no, it's not square root 3, it was 5 square root of 3. So not square root of 3, but 5 square root of 3. 5 square root of 3. 5 square root of 3. 5 square root of 3, so 40. 40 square root 3 in the end. Okay, so 292. Next, 296. So again, the portion of a plane inside a cylinder. But this again is not the vector integral, this is the scalar surface integral. So evaluate x squared plus y squared plus z squared ds, where s is the portion of the plane, z equals x plus 1 that lies inside the cylinder, x squared plus y squared equals 1. Yeah, that's still going. All right. So calculate the scalar surface integral where S is the plane Z equals x plus 1 inside the cylinder, x squared plus y squared equals 1. So this whole plane inside the cylinder bit, right, this is S, and here's the rest of the cylinder. And then if you shine the light down into the xy plane, you just get the cylinder, right? So this is the plane Z equals x plus 1. That's caught inside this cylinder, x squared plus y squared equals 1. So standard parameterization are x, y, x is x, y is y, z is fxy. For x, y in the circle of radius 1, which is the shadow this oval makes inside the xy, inside the shadow this makes in this, the surface makes in the xy plane, which is just the inside of the cylinder, which is a circle of radius 1. Okay, so the surface is the plane. The whole point of the cylinder is just to restrict the domain for the plane, right? Because you can't calculate the surface integral over the whole plane because it's an infinite domain. You want just part of the plane. So how do you define which part of the plane? Well, this is one of the cute ways in which textbooks do it. They do the part of the plane inside the surface. All right, so that's the parameterization. Of course, we need these partial derivatives. Partial derivative r with respect to x. Partial derivative of r with respect to y, 0, 1, 0. We need the length of the cross product. So first we got to do the cross product. I, j, k times, we got time. 1, 0, 1, 0, 1, 0. So this cross product is negative 1, 0, and 1. So the length of Rx cross Ry is just the square root of 2. All right, now the function f of x, y, z, it's always a three-dimensional function because the surface exists in 3 dimensions, is x squared plus y squared plus z squared. So now f of the function on the surface given by Rxy, well, x is x, y is y, and z is x plus 1. So this is equal to 2x squared plus 2x plus 1 plus y squared. So that's pretty bad, huh? $296. Yeah. So the surface integral x squared plus y squared plus z squared ds is the double integral over r of f of r of xy times length rx cross ry dA. So double integral over r, and then this is 2x squared plus 2x plus 1 plus y squared. Actually, I'm just going to leave it. I'm going to leave it like this because since the domain is a circle, we're going to have to transform to polar coordinates. So this is x squared plus y squared plus x plus 1 squared, dA. So, times square root of 2 dA. So I'll bring that square root of 2 out front. So square root of 2, x squared plus y squared plus x plus 1 squared dA, where r is 0 less than or equal to r less than or equal to 1, 0 less than or equal to theta less than or equal to 2 pi, because, we're expressing the r in polar coordinates. Right, so this is the square root of 2, and the conversion of polar coordinates, 0 to 1 for r, 0 to 2 pi for theta. Well, x squared plus y squared is just r squared, but this is nasty. This is r cosine theta plus 1 quantity squared, and that whole thing, r dr d theta. I don't see any way of doing that other than this. Conversion to polar coordinates. So this is square root 2, integral from 0 to 2 pi, integral from 0 to 1, r to the third, plus. Now, if I evaluate that squared, it's x squared plus 2x plus 1, so that's r squared, well, r to the third, cosine squared theta, plus 2r squared cosine theta plus r dr d theta. So it's 845. So this is going, well, first we do the antiderivative with respect to r. So 1/4 r to the fourth plus 1/4 r to the fourth cosine squared theta plus 2/3 r to the third cosine theta plus 1/2 r squared, r equals 0 to r equals 1 d theta. So square root of 2, integral from 0 to 2 pi, so that's just 1/4, plus 1/2, so it's 3/4, plus 1/4 cosine squared theta plus 2/3 cosine theta d theta. Oh, this is not too bad. So the integral for theta, well, first I have to use a double angle formula to get rid of the cosine squared. So 3/4 plus 1/8, 1 plus cosine 2 theta plus 2/3 cosine theta d theta. So this is 3/4 theta plus 1/8 theta plus 1/16 sine 2 theta plus 2/3 sine theta. Theta equals 0. Theta equals 2 pi. So this is the square root of 2, 3/4 of 2 pi plus 1/8 of 2 pi, and these are both 0. And then when you evaluate it 0, it's all 0. So we have root 2 times 3/2, 3 pi over 2 plus pi over 4, so it's 6 pi over 4, so 7 pi over 4, so 7 square root 2 pi over 4. That's the final answer for that one. Okay, so we did a lot of scalar surface integrals. Next time, well, I hope it does. I'll have to pick some 299, 303. No, that's a scalar. Come on, where are the vector ones? Okay, after 300, it's all vector stuff. No, that's scalar again. 305, 311. 305, that's vector. 311, that's scalar. Well, we'll have to add in some vector problems, some vector flux problems. Okay, so that's all for today. So for next time, we're going to finish up the discussion here of section 6.6 and then move on to 6.7 and 6.8. So we need to watch the lectures for those. Okay, so I'll send you an email after class. Have a good night, everyone.